Welcome to a new deep dive on the Dinosaur Stories podcast. So for this one, I want you to imagine you're walking through a late Cretaceous forest in what is now Asia.
Right, just a dense, prehistoric jungle.
Exactly. And a massive creature steps out of the shadows. Its sporting claws the length of samurai swords. I mean, we are literally talking about the longest claws of any animal in the history of the planet.
Which is an incredibly intimidating image.
Oh, totally. Naturally, your first instinct is to brace yourself for, a terrifying apex predator. But instead of hunting you down, this giant, waddling, pot-bellied dinosaur...
Covered head to toe in shaggy feathers, by the way.
Yes, covered in feathers. It uses those deadly blades to just gently pull a leafy branch into its mouth. It's a vegan.
It is, honestly, the ultimate biological contradiction.
It really is.
And to really grasp what's going on here, I want to ask you, the listener, to just completely throw out your mental blueprint for what makes a dinosaur scary, or even what makes a dinosaur normal.
Because today, our deep dive is entirely focused on untangling the wild reality of the Therizinosaurus. We are going to dig into its hilarious history of misclassification and dismantle those pop culture myths that treat it like a slasher movie villain.
Right, the movie monsters.
Yeah. And we'll explore the fascinating evolutionary mechanics that actually created it. But to understand how an animal this absurd came to exist, we first have to look at the sheer confusion of its initial discovery.
Which is a comedy of scientific errors.
It really is. So we're traveling back to 1948 to the Nemeg Formation in the Gobi Desert.
And you have to remember the Gobi in the late 1940s was an incredibly harsh environment for a paleontology expedition.
I can only imagine just the heat alone.
Oh, the sweltering heat, fighting the sand. You had joint Soviet and Mongolian teams out there just trying to extract whatever the rock gave them. And what the rock gave them was absolutely baffling.
Because they didn't find a full skeleton, right?
Not even close. They uncovered these gigantic, heavily curved claw bones. Technically, they're called unguals, which are just the inner bone cores of a claw.
Right.
And these bone cores alone were over 2 feet long. So when you factor in the keratin sheath that would have covered them in life, you're looking at appendages over 1 meter long.
Massive, terrifying sickles. But the catch is they found almost nothing else.
Yeah, no skull, no spine, no legs.
Just these huge claws and a few fragmented bone shards, which has to be like an absolute nightmare scenario for a paleontologist.
Oh, it's the worst. Because you are holding the most extreme specialized feature of an unknown animal, but you have zero anatomical context for the body it belonged to.
Right, you're just guessing in the dark.
Exactly. So you have to work via comparative anatomy. And in 1954, the Russian paleontologist Evgeny Maleev sat down to formally describe these fossils.
And this is where it gets crazy.
It really does. He looked at these massive, somewhat flattened claws and asked himself, what kind of animal uses giant flattened appendages?
Yeah.
And his conclusion was marine reptiles.
Specifically sea turtles. I'm still trying to wrap my head around that leap in logic. Giant sea turtles.
I know. It sounds absurd now. But consider his logic at the time. Turtle flippers are elongated and flattened to displace water, right?
Okay, sure.
So Maleev hypothesized that these giant flattened bone cores belong to a 15-foot-long giant marine turtle.
Wow.
Yeah, he theorized that it used these massive claws, not for walking, and certainly not for hunting, but as giant scythes to harvest underwater seaweed from the ocean floor.
That is just wild.
And he was so confident in this biomechanical interpretation that he literally named the genus Therizinosaurus cheloniformis.
Which translates to what exactly?
It translates literally to the turtle-like scythe lizard.
That is amazing. It's like finding the steering wheel of an aerodynamic sports car half buried in the mud. And because it's round like a valve, you confidently declare you've discovered a new type of deep-sea submarine.
That is a perfect analogy.
Right. Because if you only look at that one piece in isolation, your brain builds a logical but completely incorrect machine around it.
And that isolation is exactly what caused a decades-long identity crisis for this entire family of dinosaurs.
Because they kept finding more weird pieces, right?
Exactly. Throughout the 1970s and 1980s, paleontologists were finding other strange, highly fragmented dinosaurs in the same Asian formations. Dinosaurs like Segnosaurus and Erlikosaurus.
And they were just as confusing.
Completely. These animals had odd, leaf-shaped teeth meant for eating plants, incredibly wide pelvic bones, and just strangely proportioned limbs.
They were basically the island of misfit toys. Like, I was reading the source material for this deep dive, and during this period, scientists were throwing out wildly different hypotheses.
Oh, the debates were endless.
Yeah, some thought these fragments belonged to a bizarre offshoot of dwarf sauropods. You know, the long-necked, plant-eating dinosaur.
Right, because of those wide hips they found.
Exactly, but then others looked at the long necks and thought maybe they were a totally separate family of fish-eating dinosaurs that just waded in rivers.
The scientific community was completely fractured because no one had a complete skeleton. It wasn't until 1993 that the puzzle was finally solved.
The Rosetta Stone fossil.
Yes. Paleontologists in China discovered a much more complete relative named Alxosaurus. The skeleton had the leaf-shaped teeth, the wide sauropod-like hips, and the giant claws.
All articulated in one undeniable body plan.
Exactly. The dots finally connected. The Therizinosaurus wasn't a giant sea turtle, and it wasn't a dwarf sauropod. It was a massive, impossibly weird theropod.
Okay, wait, let me stop you right there. If this is a theropod, meaning the Therizinosauride lineage sits right there on the theropod family tree alongside the Tyrannosaurids and the Dromaeosaurs, right?
That is correct.
I struggle to buy this, though, because evolution usually optimizes what's already there. If you have the genetic blueprint of an obligate hypercarnivore built for sprinting, tracking, and tearing meat, how does that lineage take such a sharp left turn into becoming a pot-bellied vegan?
It's a good question.
Like, what ecological pressure forces a perfectly good predator to just start eating tough, indigestible leaves?
It really comes down to niche partitioning and the path of least resistance. In the late Cretaceous, the apex predator roles were fiercely contested by highly efficient killers like the Tyrannosaurids.
Right, you don't want to compete with the T-Rex if you don't have to.
Exactly. Competing in that arena was dangerous.
Yeah.
But the high canopy foliage, that was an abundant, virtually uncontested food source in their specific ecosystem.
Oh, interesting.
So the ancestors of Therizinosaurus found an ecological niche that was wide open, which was high-browsing herbivory. But to survive on that diet, you have to fundamentally rewrite your biomechanics.
Because plant matter is notoriously hard to digest compared to meat.
Incredibly hard. Leaves and branches are packed with tough cellulose. A sleek predator's digestive tract processes high-protein meat very quickly. But to extract calories from cellulose, you need hindgut fermentation.
So they literally had to build a fermentation vat inside themselves.
Yes. You need microbes to sit there and break down those plant cell walls over a long period. And to house that process, you literally need a giant biological fermentation vat. So Therizinosaurus evolved massive, fridge-like gut cavities.
Going back to my car analogy, it's like taking the chassis of an aerodynamic sports car and trying to bolt a massive cement mixer to the front of it.
Right, you can't just keep the sleek racing tires and the lowered suspension.
Exactly. You have to widen the axles, drop the center of gravity, and completely rebuild the foundation to support all that front-loaded weight.
That is the perfect way to visualize their skeletal shift. To support that massive, heavy gut hanging out front, their pelvic bones widened significantly. Which, again, is why scientists initially confused them with sauropods.
Makes total sense now.
And their feet underwent a radical redesign, too. Typical theropods, like a velociraptor or a modern bird, walk digitigrade, meaning they run on their toes for speed.
Right, like a sprinter.
But Therizinosaurs dropped down into a plantigrade stance. They walked flat-footed on 4 robust, weight-bearing toes, which is mechanically similar to a modern bear. They sacrificed speed entirely for stability.
Evolution just completely hijacked their body plan. And there is a recent Bristol University study in our sources that highlights just how chaotic this evolutionary branch got.
Oh, the Alvarezsaurus comparison.
Yes. They contrasted Therizinosaurs with their closest genetic cousins, the Alvarezsaurs. Both groups share the exact same ancestral starting point, but they adapted to extreme environmental pressures in opposite ways.
The divergence is staggering. Therizinosaurus went the route of extreme gigantism. They grew to 10 or 12 meters long, weighing upwards of 5 tons.
Just massive.
Yeah, and evolving massive, elongated arms specifically engineered to pull down whole trees. But the Alvarezsaurus went the route of extreme miniaturization.
Wait, how small did they get?
They shrank down to the size of chickens.
You are kidding.
No. And their arms devolved into these tiny, highly robust, stubby little limbs ending in a single thick claw, meant purely for digging into insect mounds.
So one cousin becomes a massive tree-pulling giant, and the other becomes a tiny dirt-digging chicken.
Exactly. Evolution will push biology to whatever extreme gets the calories.
That is wild. But we have to talk about the defining feature of this animal, the very thing that caused the turtle misunderstanding in the first place, the claws.
Of course.
Because pop culture has absolutely run away with how these claws were used.
You are definitely referring to the Hollywood gladiator portrayal.
Oh, absolutely. I mean, if you've played the video game Dino Crisis or seen the movie Jurassic World Dominion, Therizinosaurus is portrayed as this highly territorial slasher movie monster.
Right, the prehistoric Wolverine.
Yeah. In Dominion, it literally uses those samurai sword claws to impale and gore a giant apex predator, a Giganotosaurus. It's treated like a weapon of war. So, tell me and the listener the truth. Could those massive blades actually be used to parry or stab a T-Rex cousin?
As spectacular as that looks on a movie screen, the biomechanical reality bursts that bubble completely.
I had a feeling you were going to say that.
Yeah. Dr. Chen-Chi Liao and a team at Bristol University recently tested this using 3D finite element analysis.
Which is what? Exactly.
It's the exact same digital stress testing software that civil engineers use to see if a steel bridge will collapse under the weight of traffic.
Oh, wow. So they basically bridge tested a dinosaur claw.
Literally, yes. They took digital models of the claw's bone core, mapped the geometry of the keratin sheath over it, and applied the directional force vectors you would expect in combat.
And what happens when you simulate the thrashing weight of a 5-ton predator against those digital claws?
Catastrophic structural failure.
Ouch.
Yeah, the analysis showed that these long, narrow claws had very low shear strength. If a Therizinosaurus tried to slash or stab a struggling, thrashing predator like a Tarbosaurus batar.
Which was the local apex predator in Mongolia.
Exactly. If it fought one of those, the lateral stress would fracture the keratin sheath and just snap the bone core right at the base.
So they just break off.
Yes. They were simply too fragile for the chaotic stress of combat.
So no epic gladiator battles. If they weren't weapons of war, what was the mechanical purpose of carrying around meter-long fingernails?
Well, they excelled in tensile strength, which is the ability to resist breaking when being pulled.
Ah, okay.
So they functioned almost exclusively as a hook and pull tool. Picture a massive, slow-moving herbivore standing upright. He uses those giant claws to reach up into the canopy, hook onto thick, high branches, and just pull that lush vegetation down to its mouth.
Kind of like a sloth.
Exactly like an extinct giant ground sloth, or even a modern panda, pulling down stalks of bamboo.
So they weren't swords, they were highly specialized salad tongs.
Salad tongs is a great way to put it.
And speaking of specialized, our sources highlight a phenomenal discovery from just last year, 2025, that proves this family's hands were even more adaptable than we thought.
Oh, right. Paleontologists in Mongolia found a new cousin named Duonicus sockbatari.
And the Duonicus fossil completely rewrites our understanding of their hand morphology, doesn't it?
It really does. It's a medium-sized relative weighing about 260 kilograms. But what makes Duonicus so bizarre is that it didn't have the standard 3 fingers that every other therizinosaur has.
Right.
It only had 2 functional fingers.
Which is crazy.
Yeah, that condition is called didactyly, and it is incredibly rare in non-avian theropods outside of the Tyrannosaur family.
Right, because T-Rex has 2 fingers. And the researchers noted that its claws weren't just long hooking scythes, the joints had extreme flexion, and the claws themselves had a much tighter, stronger curve.
Yes?
So mechanically, they were designed for actively grasping and gripping branches, much like how a chameleon holds onto a twig or how an anteater grips a termite mound.
It's fascinating. It shows that evolution didn't just hand out one standard tool for this family.
No, it tweaked the shape, the curve, and even deleted entire fingers to build the perfect feeding mechanism for different environments.
Which is a beautiful lesson in evolutionary pragmatism. We humans see a big, sharp, pointy structure on a dinosaur, and our brains immediately scream weapon.
Naturally.
But nature is far more concerned with efficiency. Whether it's the giant hooking scythes of Therizinosaurus or the tight, grasping fingers of Duonicus, these were intricate tools built for securing calories, not fighting.
Okay, so if it's not a territorial gladiator, but rather a slow-moving, heavy fermentation vat using hook and pull tools to eat leaves, how did it actually live? Like, what did it look like standing in that late Cretaceous forest?
Well, let's look at the skin first.
Yeah, because you always see them illustrated online looking incredibly shaggy, almost like a cross between an ostrich and a grizzly bear. But we don't actually have skin impressions for Therizinosaurus itself, do we?
We don't have direct skin preservation for Therizinosaurus, no. But the shaggy aesthetic is highly supported by phylogenetic bracketing.
Meaning we look at its relatives.
Exactly. We have pristine fossils from a primitive, earlier cousin found in the ash beds of China called Bipiosaurus. Because the volcanic ash preserves soft tissue so well, we can clearly see it was covered in primitive feathers.
So we know the entire lineage was fuzzy. They really were giant, grumpy tickle
You could
chickens.
definitely call them that. But these weren't feathers that you'd see on a falcon.
Right. They couldn't fly.
No, these weren't complex, asymmetrical flight feathers. They're elongated, broad, filamentous feathers, essentially shaggy, hair-like quills and filaments.
Just a big fuzzy coat.
Yeah, for a multi-ton animal like Therizinosaurus, a dense coating of these feathers wouldn't be for flight. It would serve purely for thermoregulation, shielding them from the intense late Cretaceous sun or insulating them during cooler nights, and likely for visual display as well.
Okay, so picture a 4-ton, pot-bellied dinosaur covered in a shaggy coat of insulating feathers, using giant hooks to pull down tree branches.
Quite the visual.
It is, but when those branches get to its mouth, how is it actually processing the food? We know the gut does the heavy lifting with fermentation, but what is the mouth doing?
To map the jaw mechanics, researchers turned to another relative, Erlikosaurus, because we have a beautifully intact skull for it.
Oh, nice.
They ran that skull through high-resolution CT scans. Now, the CT scan doesn't just show the bone. It allows paleontologists to map the internal cranial endosteum and measure the exact volume of the temporal fenestrae.
Which are what?
Those are the holes in the skull where the jaw muscles attach. By calculating the maximum size of those adductor muscles, they determined its bite force was remarkably low. They clocked it at roughly 600 newtons.
Okay, let's give that number some real-world context for you listening. How does 600 newtons compare to other animals?
It's astonishingly weak for a dinosaur of that size. For comparison, a T-Rex generated a bone-shattering bite force of around 35,000 newtons. Yeah, 600 newtons is actually very close to the bite force of a human being.
Wait, really? That is wild. A giant dinosaur with the bite force of a person?
It proves they weren't chewing hard, woody branches or grinding up tough material in their mouths. The front of their jaw was a sharp, toothless, keratinous beak used to precisely snip vegetation.
Just clipping leaves.
Exactly. The small, leaf-shaped teeth in the back were just for gently cropping soft leaves before swallowing them whole and sending them straight down into that massive gut for fermentation. Their heads were delicate snipping tools, not crushing machines.
It really paints a vivid picture of a gentle giant. But gentle giants aren't always solitary wanderers, and the sources detail a massive discovery that completely rewrites their behavioral psychology.
You're referring to the expeditions in the Jafclant Formation in the Gobi Desert between 2013 and 2019.
Yes.
This discovery is a absolute cornerstone for behavioral paleontology.
It's mind-blowing. They didn't just find an isolated nest hidden in the brush. They documented a massive communal nesting ground.
Yeah, they found at least 17 separate clutches of dinosaur eggs, all clustered together in one specific area.
And these spherical eggs, which were measuring about 5 inches across, were positively identified as belonging to Therizinosaurs.
The implications of those 17 clutches are profound because it proves colonial nesting. We can look at the porosity of the eggshells, which tells us they were laid in high humidity environments and partially buried in organic material to incubate.
Like compost heaps.
Exactly. But more importantly, we look at the spacing. The clutches were spaced somewhat regularly, leaving just enough room for the massive adults to walk between them without crushing the eggs.
Which means multiple adults were nesting simultaneously, right? Actively sharing the same space and respecting a communal layout, just like modern penguins or flamingos.
Precisely. It reveals an advanced social structure. We have to view them not as solitary, brooding monsters wandering a wasteland, but as highly social animals that flock together.
They congregated in specific, chosen locations year after year to lay their eggs.
And by nesting in massive colonies, they employed a strategy called predator swamping. Even if egg thieves like Oviraptorosaurus stalked the perimeter, the sheer volume of adults and eggs ensured the survival of the next generation.
So, what does this all mean when we put the pieces together? We started this deep dive looking at a pile of confusing, terrifying claws that Evgeny Maleev, logically but incorrectly, thought belonged to a seaweed harvesting sea turtle.
A very creative guess, though.
It was. Then we looked at how pop culture twisted those claws into the weapons of a bloodthirsty, territorial movie monster. But the true identity of the Therizinosaurus is infinitely more fascinating than any fiction we could invent.
The reality of the animal is a triumph of evolutionary weirdness.
It is a deeply complex, highly social, feathered, pot-bellied vegan. It walked flat on its feet, congregated in massive nesting colonies to protect its young, and used the longest claws in Earth's history simply to reach up into the canopy and gently snip a salad with the bite force of a human.
Nature is amazing.
It's a perfect reminder that paleontology is a constantly evolving puzzle. A single bone can lead to decades of wild guesses, like our submarine steering wheel, until the right fossils, the biomechanical scans, and discoveries like Alxosaurus and Duonicus provide the context that reveals the truth.
And that context leaves us with a truly fascinating thought to ponder. We know from the Bipiosaurus fossils that these animals had complex skin systems that even shed as dandruff.
Ew, but cool.
Yeah, and we know from the job clamp formation that they nested in large, socially synchronized colonies. It forces us to ask, how many of the highly complex social and biological behaviors that we assume are strict hallmarks of modern birds or mammals were actually invented and perfected millions of years ago by giant, pot-bellied, scythe-wielding dinosaurs long before the asteroid ever hit?
A brilliant question to leave you with. The past is always more complex and wonderfully weirder than we give it credit for. Thank you for joining us on this deep dive on dinosaur stories. Keep questioning the history of our planet, and we'll see you next time.